Have you ever watched a human or an animal move with such grace and precision, balancing on two or four legs, even over uneven terrain, and wondered how a robot could ever achieve that same fluid motion? Legged robot motion is primarily stabilized through active feedback control strategies that continuously adjust the robot's posture and foot placement in response to internal state changes and external disturbances. This dynamic balance is crucial for maintaining equilibrium and preventing falls, especially in unpredictable environments. The core challenge lies in the inherent instability of legged systems. Unlike wheeled robots that have continuous ground contact, legged robots must manage discrete foot placements and ever-shifting centers of mass. The control system needs to constantly predict the robot's dynamic state, calculate required corrective forces and torques, and then translate these into joint commands. This involves complex mathematical models that account for gravity, inertia, and ground contact forces, all while adhering to torque limits of the actuators and friction limits at the feet. To achieve this, engineers typically employ hierarchical control frameworks. At a high level, gate generation algorithms plan the sequence and timing of foot placements. Below that, whole body controllers compute the necessary joint torques to execute these movements while maintaining balance. Critical components include estimating the robot's current state, such as its exact position, velocity, and orientation, and then comparing these measurements against desired trajectories. Any deviation triggers a corrective action through a feedback loop, adjusting joint angles and forces to steer the robot back to a stable path. A foundational concept in legged robot stability is the zero moment point, or ZMP. The ZMP defines a point on the ground where the sum of all ground reaction forces creates no moment or torque. Keeping the ZMP within the robot's support polygon, which is the area enclosed by its feet in contact with the ground, is a key principle for achieving static or quasi-static stability. More advanced techniques often leverage model-predictive control, or MPC, which optimizes future movements over a short time horizon, anticipating dynamic changes and external impacts to maintain robust stability. Ultimately, the goal of these control strategies is to grant legged robots the ability to traverse diverse and challenging terrains with resilience and efficiency. By actively managing their center of mass, anticipating disturbances, and carefully planning their movements, robots can maintain their balance, mimicking the sophisticated stability that living creatures exhibit naturally.
If you love robotics, like, subscribe, and keep building with us.